Welcome back, guys. Now that we finally have all three of our images, we can begin with the target optimization process. On a new cell in our Collab notebook, we need to define a few basic parameters to help us visualize the training process and for us to facilitate the training process. The first of these parameters is called showEvery, which is simply going to show us our target image every so often so we can check the progress of the optimization process. Let's set this as 300 so that we can get an updated image every 300 iterations. We also need to define our optimizer, and we will do it using optim.atom, as we have always done before. However, in this statement, we are going to put our target image, as this image is what requires optimization. And now the learning rate parameter, through empirical observation that I have found to work well, is LR equaling 0.003. Okay, next let's define the amount of optimization steps that our training process should take. Conventionally speaking, the more steps we take, the lower the loss value and the more effective the style transfer. We need to have a balance between results and time efficiency, as the training process can take very long to complete. I find that a minimum of 2100 steps is required for decent results. Beyond that, you can add more steps to improve your output, but we are going to maintain the minimum limit of 2100 steps to make sure that everyone can follow along and get the same results, as I know that all of you have various time constraints. If you have more time to spend, or you're simply curious, you can run your code for more steps. Let's define our steps variable as 2100. Alright, and now the next few lines are purely for data visualization post the training process. We are going to define an image array that is going to store target images throughout the training process. And after the training process, we will create a video out of these images to get a visual of how the style and content images combine to optimize the target image. This array will be empty, numpy.empty, and it will numpy.empty, and it will have a shape that resembles the shape of our target image. Let's add a preceding line that unwraps the shape of our target image. We have the heights, we have the width, and obviously the number of RGB channels. And now placing our target tensor inside of our image convert function, we can do that to get the shape of our tensor image as an RGB image. And now we can go back to our image array that we defined, and we can fill it up with dimensions. In order, we define the image height, width, and number of channels. We also don't want to store all the images throughout the training process, as that would take up too much memory on the Collab notebook. So let's define a maximum array size of 300. So what happens is we get 300 frames in total to visualize the optimization process. In order to fill this array up with the right amount of images, we are going to define a capture frame variable that will help us capture a frame every so often. In this specific case, if we want 300 total images for our output video, we simply define the capture frame variable to be equal to the total number of steps divided by 300. Doing the math, with 2100 total steps divided by 300, we will capture a frame every 7 steps to ensure a total of 300 frames. Finally, in regards to this visual data output, we are going to define one last variable called counter, which will keep track of the array index that we are at to make sure that the frames get captured in proper order within our array. And so we simply give it an initial value equal to 0. And there is an error here. Recall we used these values so that this image array will have a shape that resembles the shape of our target image. So let's explicitly specify these values as part of the shape argument. Alright, we should be good to go from here. let's begin coding our optimization process in a brand new cell. The cell is really going to wrap everything up together, so I hope you guys are ready, as the optimization process is done in steps. We are going to start with an obvious for loop that will iterate over the variable I in the range of 1 until steps plus 1. This is to ensure that our loop runs for the defined number of steps. Alright, and now the first step in this loop is going to be the collection of features for our current target image. This is done with a simple call to our getFeatures function with our target image as an argument and our VGG model. The value returned is going to be stored inside of a target features variable. And now we can calculate our content loss for this iteration. This is going to be a simple mean square error formula, as seen here. You've already seen this formula in the linear regression section. In code, this will translate into torch.mean, which is equivalent to the 1/n term in the mean squared error formula, and next we simply get the difference between the target features from the conv42 layer. Getting the difference between that and the content features from the same conv42 layer. As I was saying, as we've already mentioned, this is the layer that we use for content feature extraction. And it makes perfect sense that we're calculating the loss as the difference between the target features and the content features, since remember, we want the content features of the target image to match the features of the content image. So the greater the difference, the greater the loss. Alright, and now according to our formula, simply squaring the error gives us the mean squared error between the content of our target image and our actual content image for this specific iteration. Alright, make sure you do not make any errors on the following 2 lines of code. They are very crucial. And next we deal with our style loss for this iteration. We begin by initializing the style loss equal to 0 for this particular iteration. This is because the style loss is a bit more complicated than the content loss, as the style loss is the result of a combined loss from 5 different layers within our model. For this reason, we actually need to iterate through the 5 style features to get the error at each layer, and we then need to calculate a weighted average of this loss. So what we do is within this for loop of iterations, we specify another for loop that will go through every single layer object in our style weights dictionary. And this is to ensure that we cycle through all 5 of our style layers. We begin this loop by collecting the target feature from the target features variable. And for the specific layer that we are currently looping through, this will be done for each of the 5 layers. The next step is to apply the gram matrix function to our target feature. Gram matrix to target feature. Recall the functionality of the gram matrix. If you don't know what it does, make sure to revisit the previous video. And now what we do is we store the returned value into a target gram variable. And now similarly, we are going to get a style gram value for our style image from the previous style grams variable. Style grams from the previous style grams variable that we defined earlier, and we are going to feed this specific layer as the argument to get its respective gram matrix. Now we can simply calculate the layer style loss. Layer style loss. Similar to how we calculated the content loss. We can simply go above and copy the following. We copy and paste the mean squared error formula. We replace the target feature variable with the target gram variable. And we also replace the content feature variable with the stylegram variable minus stylegram. We want the style features of the target image to match the style features of the style image. The greater this difference, the greater the loss, and we calculate this loss for all 5 layers, which dictate our style weights. And now that we have a loss for that specific layer that we are iterating through, the one extra term that we are going to add to this loss equation is the style layer weight values that we defined earlier. As certain style layers have more weight than others, their loss values also carry that respective weights. So let's multiply our specific layer loss with the style weights of that specific layer times torch.mean, and this will scale the per layer loss appropriately among the 5 layers being iterated through, making sure to prioritize the earlier layers within our network. And now that we have a style loss for this layer, we need to add it to our total style loss for this iteration step. We are going to use the initial style loss variable we defined earlier, setting it equal to the layer style loss for that particular layer. As our second for loop iterates, the loss from each layer will pile up to sum into our style loss variable. Now we are just one additional step away from having the complete expression for our style loss. While we have obtained the layer style loss, this loss needs to be normalized in order for us to obtain the unit loss, as we applied the gram matrix to the entire layer. This is obtained simply by dividing the layer style loss variable by the product of the depth, width, and height. Depth times height times width. Now moving back by a line, what we can do is we can use the target underscore feature dot shape method to obtain these feature dimensions. We can store the shape into the batch number, which we don't need, so we will leave that as a blank, and now we can obtain the depth, height, and width. Alright, and now with each iteration of our for loop, we will sum together the style loss from each layer and obtain a final normalized style loss. So now we have effectively extracted our content loss and our style loss from the target image. Exiting the for loop, we can now combine these two loss values and use them to optimize the content and style elements within our target image. So let's set a variable called total loss, which will represent our combined content and style loss. We are going to set this equal to our content loss plus our style loss. Alright. And now scrolling up to remember that we had a style weight and a content weight. These variables become relevant here. In order to compensate for the respective weight of content versus style, we are going to multiply the respective weights with the respective loss values. So beside content loss, we are going to multiply by content weight. Similarly, beside style loss, we are going to multiply by style weight. This will weigh our loss values accordingly and result in a weighted total loss value that we can use. Alright, now that we have our total loss value, we can use our atom optimizer that we defined earlier to optimize our target image. While in earlier sections of the course, the optimization process would update parameters within our neural network, now we are using the optimizer to update parameters within our target image. Therefore, over time, our target image is going to try and minimize the total loss. This will mean that it will maintain the content of our content image by maintaining a similar output feature at the conv42 layer as our content image feature at the same layer. It will also take on more style from our style image by attempting to have gram matrices that resemble the gram matrices of our style image at all the defined style layers. This is where I will revisit the video that I showed you guys earlier. While at the time it might have been difficult to make sense of, I hope that you guys have grasped a better understanding of style transfer to make sense of it now. Essentially, you take your style image, extract its features as we did, and then take a gram matrix of these features. You then take your target image, written as random pixels here, and put it through the same process of feature extraction and the gram matrix. By updating the target gram matrix to match the style image gram matrix, you essentially attempt to extract the style from the style image and implement it into the target image. This takes care of image style. For content, you extract features from the content image and attempt to make the features of the target image similar to the features of the content image. By optimizing these two steps, you can achieve style transfer. Notice also that this video mentioned the use of the VGG16 model, however we used the VGG19 model as proposed in the actual style transfer paper. Both models are powerful and capable of producing great style transfer results. Now, while we have taken all the steps mentioned above, we need to implement the target image optimization into code. Once again, we use the similar optimizer.zeroGrad function, and we set all the gradient values from our previous backpropagation call equal to 0, essentially resetting our optimizer for this iteration of optimization. And now we use our total loss variable along with the backward command to compute all the gradients required to minimize the loss with respect to all our target image parameters. And this is how the optimizer learns which pixels to adjust and how to adjust them in order to minimize the total loss. And now finally we can use optimizer.step to update these weights for this iteration. With each iteration, our target image is going to take on more style from our style image while maintaining the content of our content image. Alright, now that was definitely the hard part of style transfer. Putting it all together, and while we've implemented a lot of code, we haven't seen much output to verify that everything is working as intended. So let's add a few extra lines for data visualization throughout the training process. We defined some values earlier for this very purpose, so we can take advantage of them now. We want to visualize our target image throughout the process to see how it's shaping up to look. So we are going to use the showEvery variable we defined earlier to show our target image every 300 iterations. We can do so using a simple if statement that will compare the II iteration variable with our showEvery variable using a modulus operator. Comparing that to showEvery, the modulus operator simply divides II by showEvery and returns the remainder of the division operation. If the mod result is equal to 0, then we know that our iteration variable has jumped 300 iterations. Using this logic, we will display the target image every 300 iterations. So whenever this if statement is true, we can print our total loss with total loss.item. And now we can also print the iteration that we are currently on. Print iteration II. And this will help us keep track of the loss and the amount of iterations that have taken place. And under these statements, we can also use the plt.imshow command, .imshow function, to display our target image. As the target image is currently a tensor, we also need to feed it into image convert before we're able to display it using imshow. And finally, we can use plt.axis to remove the axis on these images off. And finally, using plt.imshow, our image will be displayed. Using similar logic, we can implement an if statement that compares the II iteration variable with our capture frame variable, once again using a modulus operator. As we set this equal to the number of steps divided by 300, in our specific case this sets the value equal to 7, meaning that if we use the same condition equals 0, our code will capture a frame every 7 iterations, capturing a frame every so often will allow us to create a useful output video of the entire optimization process to visualize how our target image evolves over the many iterations. It should be an interesting visualization. So now whenever this condition is met, we want to store our current target image into our image array. As we don't want to consume too much memory on the Collab notebook, and images can consume a lot of data, we have limited the size of this array to 300 images. You can play around with this number as you desire, however, too many images will cause the Collab notebook to crash. So now we access our image array and set it equal to our target tensor as an argument within our image convert function to convert it to a NumPy image. And we also want to save each consecutive image at each consecutive indices within our array. As such, we are going to set the index value as our counter variable. This counter variable is going to increase by 1 every time an image is stored inside our array, so that next time the image gets stored in the next index of our array, we can implement this very simply by setting our counter variable equal to counter plus 1, or plus equals 1, whichever. Alright, now our optimization process is finally complete and ready to be implemented. Running the cell is going to take quite some time, so make sure you have your GPU enabled, as it will take even longer if you don't. Alright, first mistake, forgot a comma. Let's check for any more mistakes. Let's remove the spacing here. As we have written a lot of code, it is normal to make mistakes every now and then. This line of code seems good as well. Stylize equals 0. And one more thing, this should say plt.show, not plt.imshow. Aside from that, we should be good to go. Trying out the training process again. Alright guys, so the optimization process is complete, and you'll notice that our target image is displayed every 300 iterations as we wanted. Our target image definitely contains content from our content image, while we can also see a nice mix of style from our style image. Our image visualization worked properly, and you can see that the image gets progressively more styled throughout the process. With more iterations, the results only get better. So if you have time, I highly recommend you go for it. I personally get very good results using around 10,000 to 15,000 iterations, rather than 2100. And so here is a video of that same result using the same two images. Let me just expand that so you can get a nice visual. Pretty nice. This was done with 10,000 iterations. Let's plot our content, style, and final target image side by side to see how the content features merged with the style features using the familiar plt.subplots function. We are going to make a grid arrangement with a single row and 3 columns for our 3 images, and we'll define a fig size equal to 20 by 10, and storing the subplots call into the appropriate fig variable along with the 3 axes, axis 1, axis 2, axis 3 for each image respectively. And now let's plot the content image on the first axis using ax1.imshow image convert. We will plot the content image first and foremost. This essentially converting our tensor to a NumPy array, and we'll also access axis 1 and set the axis value to off. And now copying these 2 lines twice, we change axis 1 to axis 2 in both lines, and replace content with style to plot our style image in the second axis, and finally we repeat the same process for axis 3. And plot our target image. Now running this cell, we can view all 3 of our images side by side. It's cool to see just how the content elements and style elements have merged. What an amazing technique. I highly recommend you guys try other pairs of images for unique results. It's really phenomenal stuff. You can feel free to end this section here. However, I'm going to add one additional cell to show you guys how I exported that video that I played earlier. This video shows the optimization process in action and demonstrates how the target image evolves over time. So if you are interested in exporting similar videos for your results, then stick around. We will do that in the next lesson.